You can also access this microphone. The microphone is also for...
Yeah. Hello everyone, I'm Tarek and we are top Team Northeastern. So our presentation is going to be about two parts. In the first place we are going to show our manipulation framework, and in the second part my teammate Naoki is going to present our visual perception architecture for finding and describing the people. So in the first part I'll talk about our manipulation framework, where we are trying to solve two problems in one manipulation framework, where we are trying to so we have two goals. First, we are trying to develop an integrated grasp and motion planning, where the robot solves the grasp planning and the motion planning problem at the same time. And we also want this system to solve sequential manipulation task, where the end effector of the robot needs to go different places in 3D space sequentially, and we want to produce a complete trajectory without robot stopping while doing these manipulation tasks. So to be able to do that, we define the motion planning problem as a trajectory optimization problem, which is a non-linear, non-convex constraint optimization problem, and we are solving this problem using sequential quadratic programming, where we minimize the sum of the joint displacement between each waypoints, and we define the end effector positions as the inequality constraint, and this allows us to do the grasp planning, because based on the object geometry we can create a grasp space around the object, and this can turn into a optimization constraint, and then we can solve the problem. So I'll do a quick demonstration, and then actually let me talk about this. So go ahead. No. Perfect. Yeah. So this is some of the tests that we have done in the lab. Over the 15 trials, we observed that using our framework with respect to the two-step planning, where robot is planning for picking and placing in two steps, our framework is a lot faster in terms of execution time. You can see that over 15 trials, one-step planning was around 20 seconds, and the two-step planning time was around 27 seconds. So we'll do a quick demonstration. So as you see, the robot is going to pick and replace object without stopping. reception part.
Hi, my name is Naoki. I am the machine learning and computer vision lead at Northeastern. So first I'll talk a little bit about our natural language understanding framework. So our process is we want to make sure that the robot can be flexible and understand a wide range of commands and vocabulary without having to hard code any kind of rules or rigid grammars. So we use Google NLP's recurrent neural net to identify the category of each word, not based on their spelling, but more on their conjugation and their context within the sentence itself. And then we use the word-to-vec neural net in order to map an unknown or a detected verb that we get from the sentence to a task that the robot knows how to do. Word-to-vec basically transforms every verb into a numerical representation representing their meaning. So we get a word we can match a word to a task that the robot can do that's very similar, even if they're spelled completely differently. And then for special commands and questions and prompts and keywords like object detection labels, we use the Levenshtein distance in order to see how different each the word that we get or the phrase that we get is from our dictionary. So if we get like Oreos instead of Oreo, we can easily match and say, okay, that was 99% correct, so that's what it is. Okay, next is our main task is visual perception for person description. We did a lot of our tasks for EEG-DSR. So the central component of this is OpenPose. OpenPose is a real-time person detection framework that can detect many people and their key points regardless of how many people are actually in the frame. So we also use the gender and age classification based on the face that's detected by OpenPose. So this neural net is a convolutional neural net that can detect the gender and age of the person and is trained on the data set that is very blurry, has a lot of occlusions, distorted in various ways. So it's very robust, especially when you're dealing with grainy webcam images like ours, like on our robot. We have another emotion classification neural net made by a German team from last year. And this is one of our other central contributions. We trained a neural net on a deep fashion data set provided by the University of Hong Kong with around 300,000 images of different categories of clothing. We use the Inception V3 architecture, which is an ensemble of different convolutional neural nets pre-trained on the ImageNet data set. We also generated a lot of artificial training images when we're training our convolutional neural nets so that it's more robust against overfitting on the training set. So what I mean by that is, for every image that we do in deep fashion, we distort it in several different ways so that it understands different ways that object can be represented. So we can rotate it a little bit, we shift it a little bit, we shear it a little bit, and for object detection, which is like YOLO darknet, what we do is we create artificial images where objects are placed randomly on background scenery. So these images on the left were randomly generated, and the objects were placed, and their bounding boxes were recorded, and then on the right, you can see how the results are evaluated on the test set. Next we also have color detection, which is basically we use a histogram on the OpenPose skeleton to see exactly what color every clothing is. And yeah, so now we'll show you a demonstration.
We are going to need 2 volunteers from the group, and it would be great if we can get a lady as well. Just need to stand in front of the
Yeah, thank you. I ran it. HSR, please analyze the
Okay, everyone, please assemble the electronics. Make sure.
Time is up.